All right. So in our pre-work, we basically learned everything I want you to immediately take from exact ODEs. I want to review, see if there's any questions, and then I want to do one extension from this. Okay? So in our pre-work, we saw that, say we started with a function psi sub xy. It's a differential function. And suppose we have a first order ODE written in differentiable form. So it looks like psi sub x of xy dx plus psi sub y of xy dy equals 0. So that's that differentiable form. Here, notice I've got, this is playing the role of m, this is playing the role of n. So we saw that this is an exact ODE. And its solution is just psi sub xy equals, let me write this, psi sub xy plus c equals 0 is the solution to it. So as soon as you identify this function that you can think of as creating the ODE in differentiable form, that's it, you're done with the problem. Okay? This should ring a bell if you've had Calc 3. This was the same thing as saying, this is very similar to saying we had a potential function for a vector field. Okay. All right, in our pre-work we gave a procedure for solving the exact ODE, which we'll review in just a second. Please know, so this is something very important, folks. This happens on tests all the time. Please know this method assumes, assumes you've already verified that the ODE is exact. So you can't use this method, you can't use this technique unless you've already said that the ODE is exact. So that's, if you think that you're going to be doing this method, you think the ODE is exact and you're going to find this psi sub xy, you need to first verify that it is an exact ODE before you go further. Okay, so here was our solution, let's see here, or here was our testing for determining whether or not an ODE was an exact ODE. And the way it went was this: if our m sub y equals n sub x, and those are both continuous, then we can go ahead and say that the ODE is exact. Again, I could always write an equation in differential form. Excuse me. I could always write an equation in differential form, but that doesn't mean it's exact. You verify it's exact by checking this statement here. Okay? Please, folks, m's and n's kind of can be confusing alphabetically where you put them. Okay? It's you take the partial derivative of the expression in front of differential x with respect to y, and you take the partial derivative of the expression inside of differential y with respect to x. And if you have equality, that gives you something called equality of your mixed partial derivatives. And if that's the case, then that ODE is exact. Okay? So this is saying that we're guaranteed to be able to find a psi of xy, provided these are all continuous and we have equality of mixed partial derivatives. If you'd like more of a discussion on that, I'd be happy to provide it, but I feel like this is, after we describe what an exact equation is, we kind of just get into a kind of a plug and chug mindset for doing these problems. If you'd like more of a discussion, feel free to come by and see. Okay, so my question here is to verify that this differential equation is exact, and then solve for the y sub x, putting your answer in explicit form. Let's have you all try that. Let's at least get started with that, verifying that this is exact. Keep working on it, but if you're dead stuck, I've given you a little bit of a hint there for getting started. So folks, if you're dead stuck, recommendation is to rewrite this as dy dx, and then think about, what do they call that way back in grade school? Cross multiplication, right? Doing cross multiplication with this. Okay? And so we get 6y squared minus x squared plus 3. Okay? Technically, folks, I need a parentheses on that, right? Because all of that's being multiplied by the differential y. is equal to negative 3x squared minus 2xy plus 2 differential x. How are we doing? Okay. Now let's go ahead and collect things over. So we have 3x squared minus 2xy plus 2 differential x plus 6y squared minus x squared plus 3 differential y is equal to 0. Finally, I've got it in this differential form. Okay? I think that one of the things I want you to practice doing is moving things to their correct form. I used to get, when I took differential equations, they would say, solve this equation. I'm like, well, it's got to be exact because I put it in differential form, that's what I'm going to do. But then when I saw something like this, I wouldn't even think to check to see if it was exact and try that technique. So that's why I'm making you do some manipulation of these to just kind of keep that avenue of thought open. Okay, so now we want to go ahead and we can identify that our let's just take the part, let's go ahead and call this m. I'm not going to recopy it. We'll call this m. And so m sub y would be minus 2x. And let's take this, and then this would be our n. And so then our n sub x is also minus 2x. So m sub y equals n sub x. So the ODE is exact. That means that we can now apply that technique that you learned how to do in your pre-work. That's already written way too big.
I'm just curious, like how you got the negative 2x?
Yeah, let's talk about that. Oops.
And you
Let
did
me just
partial
fix the size of this
derivative.
here, Chandra, and we'll take a look at that. So what I'm doing here is this is my m, and notice that subscript y there.
Yes.
That's shorthand for saying I'm taking the partial derivative of m with respect to the variable y.
I see.
How's that work? Okay. And so what is the partial derivative of this with respect to the variable y?
2y?
That's a 0, that's a
Y.
0 because they're constant as far as y is concerned, and we got minus 2x.
Y, yeah.
Okay. How's that work? Okay. And so just to spell it all out, what would this be? This is partial n, partial x. Great. Other questions on that, folks? I appreciate the question. Just folks, if you have questions, let me know. That's kind of why we're able to do some work and pre-work, and now you know already a little bit about what you want to ask. All right. So let's go ahead now and use this technique. So we're going to integrate. I'm going to integrate m with respect to x, or what else could I do? I could integrate n with respect to y. You can do it either way. I have seen instances where one way is easier than the other. I probably won't mess around with that here. So I would just take one of your component functions and integrate it with respect to the variable that it was written with respect to. So let's see here. That would be the antiderivative. Oh, help me out here. Folks, I need you to read that to me. I can't keep scrolling around. What was the m? It was 3.
Minus 2xy plus 2.
Do I have that copied correctly, folks?
Yes. Yeah.
Okay, so integrating this gives me x cubed minus x squared y plus 2x. And then what did we always write in Calc 1 when we took the antiderivative? We put plus c.
I want to make sure we're using the right equation. Didn't we label that as?
I don't know. Sorry, I can't. Yeah. So my m was the 3x squared minus 2xy plus 2. So I think we're okay.
I have it reversed on my notes. That was my bad.
That's okay. That's okay. It doesn't matter. So regarding labeling, notice that I'm integrating the component function with the differential x. That's what I'm integrating. Or I'm integrating this one with the differential y. So it doesn't matter whether I call it m's or m's. I'm either going to integrate this, because it's the coefficient function, or it's the function in front of the differential x with respect to x, or I'm going to integrate this with respect to y, whether it's m or n. And I probably am not consistent with what I call m and what I call n one day to the next. Great, so we okay with that? So, way back in Calc 1 though, folks, we said, okay, because this is a whole family of functions that would have a, if this were a 1 or this were a 2 or this were a 3, if you take the derivative of this with respect to x, you'll end up with your integrand. But because these are multivariable functions, what do I need to put there?
C.
CY.
c sub y, because it's a constant as far as x is concerned, but there may be the expression may involve y. Okay? All right, so then what I'm going to do is I'm going to take the partial derivative of this with respect to the other variable. Okay? When I do so, when I take that partial derivative with respect to y, I end up with minus x squared plus cy sub y, where that subscript there says I've taken the partial derivative of that with respect to y. Okay. Let me back up just a second. If I knew what this c sub y was, I'd be done with the problem. I would have my original psi of xy. So the issue is I just need to figure out what this unknown expression is here. So what am I doing? I'm taking the partial derivative of this with respect to y, and now I'm going to look and I'm going to compare this to the component function in front of differential y. Okay? So if I go look and compare that to the component function in front of my differential y, I have 6y squared minus x squared plus 3. So we're comparing those two together. So here is my 6y squared minus x squared plus 3, and I'm comparing this to this minus x squared plus cy of y. And then what we do, and this is a very classic thing to do in this class, we make a positioning argument. Okay? On one side of the equation, I've got this expression and this expression, so those two expressions are the same. And so what do I know? My cy sub y is what's left. Do I have a question? Oh, yep, you pointed it out. Great, great. Okay? And so I get that my 6y squared plus 3 is the partial derivative of that expression when I took it with respect to y. So now I'm going to integrate this expression with respect to y. So we take the integral of 6y squared plus 3 with respect to y, and that's equal to the integral of cy sub y with respect to y. And so that tells me that my c sub y, the one thing I needed still to be able to give my solution to this problem, is 2y cubed plus 3y plus c. So again, we knew a large chunk of the answer when we integrated the first component function with respect to the first variable. The only thing we didn't know was what this expression that only had y's was. Now we found it, and so I'm ready to give my entire solution. My psi sub xy then is so much scrolling. X cubed minus x squared y plus 2x plus 2x, and then plus this. So plus my 2y cubed plus 3y plus c. That's my psi sub xy. Now, when I'm doing this, I'm only looking for, so at this point, well, we'll just leave it at that. So my solution then to this differential equation is the implicit solution and oftentimes we park it like this. Other times you might solve it for the c. I don't care how you park it. Well, I'm sorry. I'm not going to give you a general rule always where to park it. Each problem, if I want it parked this particular way, I'll tell you how to do that. Okay? Notice that I can still solve an exact IVP if I had an initial condition. Okay? If I had an initial condition like the order pair of 0, 1, I could plug in 0 everywhere I saw an x, a 1 everywhere I saw a y, and then I could solve for my unknown c there. Okay? How are we doing, folks? We feel okay with this? A little, take some practice?
I just have a question. Again, when we pick the formula, do we pick? I don't know how to ask this. Can you scroll up a second?
Yeah.
Um,
And I was trying to fit this all in one page, so I was kind of zooming in and out the whole time.
So we took, let's see. we said m was 3x squared minus 2xy plus 2. But why? Okay, hold on.
So let's not think about it in terms of m and n. Let's think about it in terms of the variables. The coefficient function in front of differential x was this. So I integrated that with respect to x.
Right.
Okay.
Okay, I was trying to figure out what happened to the negative sign, but I guess we dropped that one.
Did I make a mistake? Oh, this minus sign. This one right here?
Yeah, I guess.
So remember, so to put this into differential form, and this is where I didn't want to distribute this through,
Right.
because there's just too many, because when I add it over, I've got way more, I've got 3 negative signs or 3 signs I gotta be keeping track of. So I just left it there. You could have distributed it through, but then you would have added the whole expression over, changing the sign of each one of those terms.
Right.
But instead, I added it over to this side, and so that's why we don't have a negative there.
Okay, that makes sense.
So, well, it doesn't matter which side I collect everything to. You could have subtracted this over as well. So somebody else doing this problem may have opposite signed m's and n's than you, but you need to stay consistent with that. So I chose to collect everything over to the left-hand side. I could have collected everything over to the right-hand side. So if you had brought this over, your function may look slightly different in the process, but eventually it'll come out in the wash.
Okay.
Yeah. So like throughout the process, everything might have had different signs. But in the end, I think you would have the same thing.
Okay.
Yeah.
So does it not matter because my equals nx, so then it's just kind of interchangeable?
Correct. Well, that's kind of part of that. That boils down to part of that procedure. Yeah. Yeah. So let me just point out here, folks, I guess let me say it like this, make sure I don't know if I've convinced you. Let's say, so here I've gotten down to this solution. If I were to multiply both sides of this equation by -1, are we still true? Yes. And so that's why somebody else might present it. The way they present the solution may look slightly different, but it'd always just be, so like that would affect, it all works out in the wash there. Does that make sense?
Yep.
Yes.
This is more a general question, but what does this tell us? Like, what is this answer?
Just come
Well,
like this.
so what I'm saying here is that if you were to take the derivative of this with respect to y, and in this case, because I've left it in implicit form, and I do not want to try to solve this explicitly, I've left it in implicit form, I would differentiate both sides. Sorry, I think I said with respect to y. I would differentiate both sides with respect to x on both sides, but that would introduce a y prime term somewhere in here by the chain rule, by implicit differentiation. If I then solve for my y prime, I get an expression, and I could show that this expression on the right-hand side is equivalent to it.
Okay.
So this is where, we've done this a couple times where we didn't find the solution explicitly. Here it would be a real mess. Not because it was an exact equation, but just because of how large it was. Because of these cubes and et cetera that show up here. It'd be a real mess to try to solve for y explicitly.
Okay.
Good questions. All right. Next page. So go ahead and I'd like you to use that method. I'd like you to try to solve this one.
So,
You can't do this problem using the method I just showed you. Why not? Yeah, so what's the very first thing we need to do with any equation if we're going to use the method for solving exact equations? We need to do what?
Determine it's exact.
We need to verify that this equation is exact. So this would be playing our role of our m here, and if I were to take m sub y what do I get, folks? I get 3x plus 2y.
Yep.
And then if we were to call this our n, and if I were to take n sub x, what do we get? We get 2x plus y. What?
Not equal.
Those are not equal to each other. So m sub y, we do it a different color. M sub y does not equal n sub x, so the ODE is not exact. Okay. If I had more time, I'd let you, for those of you that hadn't checked that, you were well on your way in the procedure. Eventually you would get stuck. You say, I can't make these things equal. You'd eventually get stuck. Okay. So the first thing you need to do is verify. That's why, even if it is exact, I still require you to show me that the ODE is exact before you use this method. Does that make sense? Yeah, Jeremiah.
Real quick, this is like an arithmetic thing, but how do you get the dx over that term?
Oh, yeah. So folks, whenever you're having trouble with that, remember that we can think of this as dy over dx. And then I can think of, and this is, I'm not going to get into how you'd actually make this happen, 'cause it's kind of a lengthy argument, but I'm going to multiply both sides of this equation by differential x. So that would give me a differential for x for that first term. The second term, the differential y over differential x, and multiplied by differential x. We can think of those as if they were fractions and we were canceling them. And on the right-hand side, we just have 0 differential x. So that's how I got there. Great question. Other questions, folks? Okay. Now, folks, this is kind of an advanced problem. It's not super hard, but this is what I need you to know. Okay. I don't really have any more to tell you about exact ODEs besides what we did in this one and the 2 or 3 examples that you worked in your pre-work.
Right.
Not much else to say about it. Okay. This is a nifty situation here. I discovered this in a handful of books. It's not in our book. Okay. I'm going to go ahead and multiply both sides of this equation by x. Why? We'll talk about that down below. Okay. But let's first multiply both sides of this equation by x, which is a legal move, right? As long as x isn't 0,
on both sides.
that's a legal move. And so we end up with 3x squared y plus xy squared plus x cubed plus x squared y prime equals 0. Putting this into differential form, we get this. And now checking, let's label this as our n, just to not be consistent. Our n sub y would be 3x squared plus 2xy. And we label this as m. Our m sub x is 3x squared plus 2xy. And we notice, well, the original ODE was not exact. By multiplying both sides by x, we forced it to be exact. You will not always be able to do such a move, and you should have a question. What's your question?
When are we allowed to have this?
Why are we allowed to do this?
When?
When?
How do you know?
I think it's the
How
same
do you
question
know?
we have earlier, didn't it?
So let's go through like this. The ODE was not exact,
Right.
and
Because
then I said let's multiply both sides by x.
then it is
How do you
exact
know
now.
how to do that?
That I think that's the question you asked. How did we know to multiply both sides by x?
That's not,
So I think it's legal to multiply both sides by x, but how did we know that would create an exact ODE? And the answer is down below here, although I believe I have. Okay. So, folks, that's kind of all I have to do with exact. I really feel like the topic of exact ODEs is kind of a one-off topic. Okay? I'm not saying that I won't ask you questions about it again. You'll have an exact ODE question on your first exam. You'll probably have one on the final exam, but we're not going to do a whole lot more with those. Okay? I just don't have anything more to tell you about them. Okay. Any questions though before I move on? Yeah.
So when we're going through the process, we put it into like differential form. We
Yes.
confirmed it.
it is exact.
Uh-huh.
What exactly are we doing? Like, how are we manipulating the equation when we integrate like MD x?
So what we are doing is, so exact ODEs have this property that they came from this function here. You're able to create them by differentiating this expression first with respect to x and call out the coefficient in front of dx. And then you differentiate this function with respect to y, and you call that the coefficient function in front of dy. So solving the exact ODE is the same as just finding the function that generated the question to begin with.
Okay.
I feel like that's not a great explanation, but that's the best I can do. Yeah. Good question. So the process, so this whole process here of integrating this coefficient function and then differentiating again with respect to the other variable and then integrating it a second time to give is all just a process to find this psi of xy, which if it's exact, then we knew there was one out there and we just found it. So solving the ODE is just finding that expression. I wish I had a better answer for you. I don't. There's good answers out there, but I don't feel comfortable with it. All right.